Okay, stat stars. In this screencast, we're going to learn about combinations in probability. So here are the learning targets. We're going to learn what combinations are, and then we're going to use them to calculate probabilities, and then we're going to combine it with the multiplication counting principle to calculate probabilities. So quick review, permutations are where the order matters from the group that you're picking out of a larger group. And then combinations, we're going to use them when the order doesn't matter. So let's say I decide to randomly take 3 students' homework papers from my statistics class, and I've got 16 girls in the class. I put all 16 names in a hat and draw out 3 names. How many different ways can I choose 3 students' papers? Well, it might be tempting to use a permutation, 16 times 15 times 14, but that's not going to work because is there really a difference between, let's say I pick Whit, Lizzie, and Alexis, or Lizzie, Whit, and Alexis, or Alexis, Whit, and Lizzie? They're all the same 3 girls, right? In other words, the order doesn't matter. Okay, so what I need to do is take the permutations, the 16 times 15 times 14, and divide it by how many ways I can arrange that group, 3 times 2 times 1, and I end up with 560. And so this is called finding the number of combinations of 16 students taken 3 at a time. And we're going to write that as 16C3. You might see it in some textbooks like that also. So here's our definition of what a combination is. So a combination is a set of individuals chosen from some group in which the order of selection doesn't matter. Okay, that's the real key right here. The order doesn't matter. You're going to use combinations. When order matters, you use permutations. When order doesn't matter, you use combinations. The notation NCR means the number of different combinations of R individuals chosen from the entire group of N individuals. And here's the formula. It's just the number of permutations divided by R factorial. Now, we're going to use our calculator to do this, so you don't need to memorize that formula. And where do we get it? Well, you're going to go to Math, and then Probability, and number 3, right below Permutations, is Combinations. So let's do an example. In the New Jersey Pick 6 Lotto game, a player chooses 6 different numbers, and they can be any number from 1 to 49. And the 6 numbers don't have to be in any order. As long as she gets the same 6 numbers that come up in the lottery, then she wins the jackpot. So how many different possible sets are there? So this is a combination question. And so I am simply going to go to Math, over to Probability. Number 3, we have 49 numbers to choose from. And we want to get how many ways we can get 6 numbers out of that. And that is our answer. So I'll grab that and put it down there. So there's a lot of different ways to get 6 numbers out of 49. Okay, so this whole chapter has been concerned with probability, and now we're going to bring that into our counting principles discussion. So remember that in general, the probability of an event A happening is the number of ways A can happen divided by all the possible things that can happen in the total sample space. So we're going to use combinations to figure out A and also to figure out the denominator. Going back to our New Jersey Pick 6 Lotto game, how many ways can we choose all 6 winning numbers? Well, just one way. Okay, so we have 6 numbers to choose from, and they have to all be the right ones. So that's going to be one way to do that, divided by the total number of ways to choose 6 numbers from 1 to 49. We just calculated that, so it's 1 over 13,983,816, and you get a very, very low number. In other words, you are very unlikely to win the lottery in New Jersey. Okay, let's do an example that's a little closer to home. Let's say you have 28 students in a statistics class. 16 of them are seniors and 12 are juniors. and suppose the teacher randomly selects 3 students' homework papers to grade. What is the probability that all 3 students chosen are juniors? Okay, so we need to know how many different ways can I choose 3 juniors out of 12, and then I'm going to divide that by how many ways can I choose 3 students out of all 28. So let's get our calculator going here. And I'm going to go to math, over to probability, and I'm going to pick number 3. And on top I have 12, C3. When you're using your calculator, make sure you arrow out of the subscript, okay? Then I'm going to divide that by math, over to probability, number 3. And this time we're going to pick 3 out of 28. And there we go. So we have about a 6.7% chance that all 3 students chosen to get their homework looked at would be juniors. All right, last example. So let's say that an airline has just finished training 25 junior pilots. 15 of them are male and 10 are female, and they're going to become captains. But there are only 8 captain positions available. So they're going to use a lottery process, okay? They're going to put all the names in a hat and pull out 8 captains. So they announce the results, and out of the 8 captains chosen, 5 are female and 3 are male. That looks suspicious because there are 5 more male than female, and yet less of them are chosen. So let's see if this lottery was fair or unfair. First of all, let's figure out how many possible groups of 8 captains can be selected. So that's going to be how many ways can we get 8 out of 25. So we'll do that on our calculator here. Math, probability, number 3, 25, choose 8. Okay, so we get 1,081,575. Okay, so let me grab that and put that there. Next, find the number of ways in which a fair lottery can result in 5 female and 3 male pilots being selected. Okay, so on top, we're going to have how many ways can we choose 5 female out of 10. We're going to multiply that by the number of ways we can get 3 male out of 15. Okay, so that is going to be math, probability, number 3, and that's 10, choose 5, arrow out of the subscript, times math, probability, number 3, and that's 15, choose 3. And that is 114,660. There. Having a hard time reading that without a comma. Okay. So that's the event that we want to occur. That's the A. And this is going to go in the denominator. That's all the ways that we could get 8 captains selected. So part C, find the probability that a fair lottery would result in the selection of 5 female and 3 male. Okay, so that's the 5 female, 3 male right there. So I'm going to grab that number and I'm going to divide it by all the ways we could get 8 captains. And that is our final result right there. So we have about a 10.6% probability that we could get 5 female and 3 male. Now, if we ran a simulation, we find out that the probability that a fair lottery would result in the selection of 5 or more female pilots is almost 13%. So is there convincing evidence that the lottery was carried out unfairly? Well, remember that our cutoff is 5%. So because it is somewhat likely, there's actually 12.8% probability to select 5 or more female pilots by chance alone, we can say there is not convincing evidence that the lottery was carried out unfairly. If we had gotten a probability of less than 5%, we would say there was convincing evidence that the lottery was carried out unfairly.